In our previous algorithm, k nearest neighbors, predictions were made based on physical distance. But algorithm number 30 swaps distance for a logic of yes or no questions. This is where decision trees sit among our 50 algorithms. They fall under the classification category, designed to assign discrete labels to incoming data. Many modern classification algorithms suffer from a black box problem. They take data in and output a probability, often without an explanation of the underlying logic. For a hospital deciding on a treatment, or a bank approving a mortgage, a hidden calculation creates a liability. These businesses need to audit exactly why a specific decision was made. The modern solution to this problem was developed independently by two teams in the mid-1980s. Statistician Leo Breiman formulated a framework called CART, while computer scientist Ross Quinlan published an algorithm named ID3. Quinlan's breakthrough involved borrowing a concept from this man, Claude Shannon. Shannon was the father of information theory, and he defined a metric called entropy to measure uncertainty. Quinlan realized this math could identify the most informative questions to ask a dataset. This auditable structure uses entropy to convert raw data into verifiable business rules. The training process relies on a strategy called recursive partitioning. The algorithm splits a dataset based on the most informative question, then takes the resulting subgroups and splits them again until the data is pure. We can read the result like a map. Every internal node is a specific test on a single feature. Every branch extending downward represents an answer, and the final destination, the leaf node, holds the prediction. At the root node, 10 customers answer a primary question. Is income over 60,000? The left path recurses with an age question, isolating a pure leaf of buyers. The right path hits a depth limit, stopping early to predict no buy via majority vote. This top-down approach allows every prediction to be traced backward. You can follow the chain of logic from the bottom leaf straight back to the root. This raises the question of selection. How does the algorithm identify the optimal first question? Starting at the parent box, a 50-50 split represents maximum uncertainty of 1.0 bit. The algorithm calculates the entropy of both child nodes, weighting each by its data fraction. Subtracting this from the parent yields 0.125 bits, the exact uncertainty eliminated by this split. The algorithm evaluates every possible feature threshold and selects the one with the highest gain. Breiman's CART framework achieves the same goal using a different metric called Gini impurity. Information gain acts as the mathematical engine of the tree, ensuring that every new branch is an efficient way to reduce uncertainty. This is a diagram of a fully trained model. These impurity calculations can cascade through dozens of levels in large datasets, splitting the data until the final leaf nodes achieve purity. This model functions as both a flowchart and a spatial map. Every yes or no question helps divide the multi-dimensional feature space. The algorithm drops perpendicular lines along the axes, slicing the data into rectangles that correspond to specific leaves on the tree. This reveals the algorithm's primary vulnerability. On this depth trade-off graph, when a tree grows too deep, it memorizes training noise rather than actual patterns. To work in the real world, it must be pruned back to a safe maximum depth. The decision tree provides a transparent structure that asks informative questions until uncertainty is conquered. Next, we'll see how this entire mathematical architecture is executed with a single line of code.
We know the mathematical theory behind recursive partitioning. To actually test this logic, we have to pull it out of the textbook and translate it into code. To run this, we navigate to our Jupyter Notebook environment, specifically the decision tree implementation inside the 50 algorithms repository. The first thing we need is raw material. We use the Python data analysis library, pandas, to ingest a file called social network ads. This is our historical ledger of user behavior. Before the algorithm does anything, we divide this data. First, we isolate the independent variables, our features, the customer's gender, age, and estimated salary. Then we define the target label we want to predict, the purchased column. 1 means bought, 0 skipped. Separating the descriptive features from the target outcome is mandatory. If you don't physically separate the answers from the test questions, the algorithm can't begin its hunt for the hidden correlations between them. But giving an algorithm access to historical data introduces a massive risk. We have to be absolutely certain our model is actually learning a predictive pattern, rather than just memorizing the specific spreadsheet we handed it. To prevent this exact type of memorization, we rely on a mechanism called train-test-split. We take our entire pool of historical customers and slice off a random 25%. We hide this data entirely to become our sterile testing arena. The remaining 75% is our training data. This is the only information the algorithm sees during its construction phase. With the data secured, we summon the algorithm into existence by instantiating the decision classifier. But we don't just turn it on, we have to constrain it with specific parameters. This diagram illustrates exactly what our first parameter, criterion equals entropy, does. It commands the model to use the information gain formula to evaluate every possible split, mathematically forcing the tree to always choose the question that drops uncertainty the most. Next, we set random state equals 100. This acts as a strict lock on the algorithm's internal random number generator, ensuring that any other programmer running this exact code will get the exact same tree. Then we apply the most critical leash of all, max depth equals 2. This hard codes a limit on how many consecutive questions the tree is allowed to ask. Without this limit, a greedy algorithm will drill down endlessly. It stops finding broad trends and starts mapping pure statistical noise. Finally, we trigger the execution step. We call .fit and unleash these parameterized rules onto our 75% training block. Calling fit is the moment the machine actually learns. It executes the greedy partitioning math in a single massive pass through the data and permanently stores the resulting flowchart inside the classifier object. Now we test our logic. We execute the .predict command, feeding the algorithm the data from the 25% of customers it has never seen. This graphic demonstrates the mechanical reality of that prediction. The algorithm takes a new customer's age and salary, drops them into the root node, walks them down our short 2-hop flowchart, and lands them on a final leaf labeled either buy or skip. To grade those predictions against reality, we generate a confusion matrix. This is the ultimate ledger, separating the algorithm's true successes from its actual mistakes. From this matrix, we extract 3 specific metrics: accuracy, recall, and precision. In the real world, a marketer uses these numbers to weigh their trade-offs. You have to balance the desire to catch every single real buyer, which is your recall, against the cost of annoying non-buyers with false positives, which lowers your precision. But here is the ultimate advantage of this specific algorithm. If you look at the printed tree, it isn't a black box. You can literally read the learned rules in plain English. The math outputs visible, discrete thresholds for age and salary. This elegant transparency makes a properly constrained decision tree incredibly powerful for human auditing. But its inherent vulnerability to catastrophic overfitting if left unconstrained establishes a hard boundary. It tells us exactly when this tool should be used and exactly when we need to abandon it for something stronger. When you move machine learning code from a notebook into a production environment, you can identify the precise threshold that triggered the denial. From an engineering standpoint, decision trees require minimal data preparation. They can ingest a spreadsheet of numerical values and categorical text directly, without needing the developer to manually scale or normalize the data first. The algorithm also performs automatic feature selection. It mathematically identifies which variables carry the most weight, such as a patient's heart rate or age, and naturally places them at the uppermost node of the structure. In clinical settings, doctors often rely on these deterministic paths. Seeing the exact decision boundaries allows them to verify the model's logic against their own professional experience, rather than trusting an abstract probability score. A decision tree's utility is defined by the human trust and regulatory accountability it generates, which often outweighs the need for higher raw predictive precision in a production stack, stopping growth exactly where the model generalizes best. Even with a capped depth, a single tree is unstable. Because each split depends on the one above it, changing just a few rows of training data can cause the entire structure to collapse and rebuild in a completely different configuration. We also see a geometric limitation, known as axis-aligned splits. Because the tree only draws horizontal or vertical lines, it struggles to model diagonal relationships, approximating a smooth curve with an inefficient, jagged staircase boundary.
This occurs because the algorithm is greedy. At every node, it only calculates the best possible split for that specific subset of data, with no mechanism to ensure that a local choice leads to the best global tree structure. The orthogonal splits and greedy logic that make a tree easy to audit are the same factors that make it a fragile predictor when used in isolation. This leads to a clear deployment rubric. Engineers should use a single tree to establish a fast baseline, process mixed datasets, or satisfy stakeholders who require total interpretability. Conversely, avoid a bare decision tree if your primary goal is raw accuracy, or if your data contains highly complex nonlinear boundaries. For a deeper look at balancing these deployment trade-offs, you can reference 50 algorithms every programmer should know. Chapter 7 provides the mathematical breakdowns for these classifiers, and the companion code repository contains runnable notebooks to test these splitting criteria yourself. This leaves us with a practical engineering problem. How can we overcome the instability of a single tree without losing its foundational logic? The solution involves growing an array of diverse trees on different subsets of data and forcing them to cast a final vote on the outcome. This strategy, sacrificing the transparency of one tree for the collective accuracy of many, is the mechanical logic that defines the random forest.